Hi everyone, welcome back to the second session of the workshop, and I hope you all enjoyed the first session. So we are going to do some practical aspects of analog IC design and teach you the very basic hello world introduction. And we'll start off with the analog IC design flow. So Imasha will be introducing the very basics of how to get started with analog IC design. Imasha, you can go ahead.
Thank you. Hello everyone. Immersion Mal from the third year in engineering, my internship as a research
Uh,
engineer in Silicon Technology
Imasha,
Labs. So in this section,
you have a
sorry,
small lag. Maybe you can turn off the video. It'll help with the
oh sure.
audio.
Sorry for the interruption. So let's dive into the analog IC design flow and OSIC tools. In this section, I will give you a brief introduction of the basic overview of the process of designing a chip. In this, we are going to use a node gate as our basic example. I think most of you know what is a node gate. Just in case if you don't know, a node gate is a simple logic device that inverts the input and output the opposite of it. So if you input a low, it output a high. So that's also the basic idea about the node gate. So why we use inverter as the start of our project? Inverter is very basic design. So it's kind of the hello world of the analog IC designing. So I think it may be the best option to start your analog IC design with an inverter design. Just in case, if you don't know and just not familiar with inverter designs, there are many more methods to design an inverter. Just by using a one BJT or just using a resistant BJT, but using CMOS, there are many methods. So if you are a newcomer, just searching about it will give you more insights about the IC designing. It's just an opinion from our side. So then in these sections, we use this architecture of the inverter as the schematic of our inverter. So here we use a one PMOS and a NMOS. If the input is high, the NMOS conduct the current and the output is a low. Vice versa, the input is low, PMOS conduct the current and the output is high. So very briefly, how do you think that schematic mapped into a silicon vapor? Yeah, definitely, that's a very huge process. But in a very simple manner, we can conclude it as basic 4 steps. You have seen what's schematic design. Then we have to map that schematic into the silicon vapor, that is layout design. There, we check what we can achieve and what are the post layout situations in our design. Then we have to fabricate our chip. That means we have to do our design on the silicon wafer. This can be done in foundries like Intel or IHP. You may have heard about them, and you will get a good information about those in next sections. Then when we talk about ICs, you all have seen that plastic package with metal pins. That's the next step after the fabrication. We have to separate the dies and then do wire bonding, and then we have to package it as what we see as IC. This is a very overall and basic idea about IC designing. Then after this, let's dive a bit into the analog IC design flow and the OSIC tools that we use in this flow. The first step is design specification. Yeah, definitely we have to do that before the schematic, then the schematic designing. Further notification from our side. In this course, we use in this course as our open source IC designing tools, we use the tools which we can get from the IIC OSIC tools Docker image. So after this section, we will have a guidance to install the Docker and use those tools seamlessly. So don't worry, we have covered you up. Our first step is schematic entry and netlist. As you've seen before, first you have to design the schematic of your IC. Seems very simple, but definitely there are a lot more things in schematic designs. Normally, we use Xchem or QUCS as our open source tool for the schematic designing. The main task of the schematic designing softwares are generating the netlist for the particular schematic. There are several types of netlists named SPICE, VHDL, or Verilog. SPICE files are mainly used in analog designing, and the VHDL and Verilogs are used in mixed signal and digital designing. Here you can see a basic inverter design done in the Xchem. Furthermore, when you talk a bit about Xchem itself, it's a purely optimized open source software for designing very large systems. It can handle different PDKs. You will get a good idea about PDKs in upper sections. Xchem can deal with PDKs like Skywater and IHP, and it supports several types of netlists. Furthermore, here you can see a simple RC circuit and a netlist of it. Here you can see, if we get R2 as an example, this netlist mentions that it's connected to out and int and the value of it. Likewise, netlist contains every possible data about your schematic. So then in next steps, those softwares can identify the schematic using that netlist. Our next step is simulation and analysis. So after designing our schematic, we have to know that it can perform as we thought. So in this process, we mainly use ngSpice as our simulation software, and it can perform various types of analysis, named DC, AC, transients, and there are several types of analysis rather than this. Here you can see a basic ngSpice input for a simulation in inverter design and the basic output of it. And we talk about ngSpice itself. We can use it in analog, digital, and mixed signal, all those kind of simulations. And the basic input for the ngSpice is the netlist we generated from the Xchem, and the output will be a waveform, a graph, or a raw data file as we wanted. Then our next step is layout drawing and DRC checking. So far, we have done with the schematic, and then we did the simulation. Now we know that our circuit can work as we expected. So then we have to map that schematic into a silicon wafer. So for that, we use K-layout and magic. In this section, we mainly focus about K-layout, and you will get a good idea about using K-layout in the upper section. So K-layout is very user-friendly and kind of very good software in doing layouts, and it can do post-layout verifications and GDS export in the end of our designs. Here you can see a ring oscillator design done in K-layout. It looks like a cartoon figure, but at the end of the day, you may figure out what are these tiny blocks mentioned in K-layout figure. So these are transistors and connected in them by metals. You may get a good idea about this at the end. After doing the layout, we have to check DRC and LVS and then post layout simulations. I think I missed the DRC part later. So DRC part is design rule check. Just think about a PCB. When we design a PCB, there are so many restrictions in fabrications. Likewise, in designing an analog IC, there are also restrictions like this. So DRCs are covering those restrictions. They ensure the good fabrication process. Okay. After doing the layout, we have to check what we have done. Simply that is our layout is matching with our schematic. Otherwise, the performance will be different of our IC. So the tool we use for this is NetGen. There we compare the netlist generated from the XChem and a K layout and then generate a report what are the differences or they are same. In the NetGen, they provide us a special feature to run the simulations with the extracted parasitics. So parasitics mean the unintended resistance and the capacitance. Simply, they are the not wanted parts of our circuit. So NetGen includes those parts and do the simulations and then tell us our schematic and the layout are same or not. And about the process, then we can simulate other electromagnetic behavior of our IC designing also. That would be very important when we design RF related circuit that as mentioned. So this is, I think you may not use this much in today's section, but electromagnetic simulations are also a very important step in IC designing process. Here you can see a sample NGSP NetGen output from inverter. Here they mention what are the matching nets, what are the devices that match, and what are the not matched. So you can get an idea about the L schematic and the layout part. I think most of you guys have worked with LD Spice kind of softwares. QCS comes in handy if you want a GUI based output with the XChem and those kind of Spice softwares. So this gives a user-friendly environment to work. And I think this will come in handy when you deal with these softwares. Yeah. So far, we have designed our schematic, then did the layout, then check our layout is matched with our schematic. Then what do we have to do? Then we have to generate our GDS2 files and give it to the fabrications. Here you can see a foundry inside the foundry, and you may got a good idea about the foundry in the last section. So K layout can generate GDS2 files, and then we send it to the fabrication. So then are we done with our IC design? No, definitely. We have to test our silicon wafer and complete it as a package. As you normally see, off-the-shelf devices we bring, chips come with a plastic package and metal pins. So the main fabricated silicon wafer is then cut into dies and then packaged into plastic packages, or there are several types of packages. So that is done after the fabrication. So far, we have talked about what the process between the schematic and the IC that we see in the marker. So I think you may have got a good idea about this on this section. So simply from schematic to GDS2 file, there is a huge process. So we may work with several softwares and several design techniques to achieve that goal, and then we can have our own IC. Thank you. And I think it may.
Yeah, I will go next, Himanshu. Thank you. Let me just get this. Okay. Can you see my screen?
Yes, sir.
Yes, we can.
Okay, it's IIC OSIC tools, right? Okay.
Yes, yeah.
Thank you. Okay, thank you, Imansha. So, Imansha did a good introduction to the analog IC design flow. And like if we look at this, so this is the website I've shared with all of you. So we have a lot of content here um, for you to refer and learn from. And Imasha basically covered about the inverter or the Hello World demonstration that we are doing today's uh, session, and basically talked about all the different steps and the different softwares that we're using to do those steps. And these are the open source tools he talked about. So you can go through all of these tools. As mentioned, they're open source. So the great thing is you can learn a lot of knowledge, even though they're not industry level. You can still learn so much, and you can do your own projects with these tools. That's the like the really valuable part of it, and it will like help you in your engineering career, definitely. The thing is that sometimes installing these tools is a little tricky. So that's where the IIC OSIC project comes in. So like the IIC or the India IC Initiative Open Source IC Tools project was introduced just for this purpose, to kind of help people easily install the tools. And it's a prepackaged Docker container that is hosted by a team led by Professor Herald Pretel from JKU in Germany. And they have a GitHub page. So I want to encourage you guys to go through this GitHub page. And they have all the steps, how to install Docker on your computer. Um, so first step is to clone this repository, and then you have to install Docker on your computer and make sure Docker is working. And then there's one more steps to enable the Docker container based on the tool. So all you need to do is, once you install, like, where's this Docker link? I don't know, it's this one. Let's see. Yeah, okay. So quick launch for Docker. So I have a MacBook. So it's a Docker like installer. So basically, just go there and install Docker. So it would look like this. So this is my Docker environment, and in the Docker environment, if you search, like if you just search for IIC OSIC, there's only one thing that comes up: H Pretel IIC OSIC. So Herald Pretel, Professor Herald Pretel's IIC OSIC Docker image or Docker container is there, and all you need to do is uh, install it here, and then like make sure it's loaded there, and make sure the Git repo has been cloned, and then you just need to run this uh, file which is in the Git repo. So if you look at the Git repo, they have a file here, start shell.sh, and if you run that file from your PC, then you're done. Like you'll be able to access ISC OSIC tools, and in the tools, they have three PDKs: the Sky 130, GF 180, and the IHP SG13G2. So we are going to use this PDK, which you'll learn about in the next session. So we'll talk about that PDK. But just to let you know, like this is the main PDK we are focusing on both for the workshop and the course. And these are all the tools they have already installed in OSIC, IAC OSIC Docker container, and all the tools Imasha talked about: Klayout, Magic, NetGen, ngSpice, um, tSpice, Qux, um, Sky 130, um, XChem, and this one. Like, yeah, all of them are here. So you can easily get access to these tools without worrying about installing them one at a time, which is very hard. And then the idea here is we have we have uploaded links to these videos, and we'll do them ourselves as well. The idea is you can use these tools and this PDK, and you can do all those steps that Lohan talked about. Imasha talked about. You can do the schematic in XChem, and then you can do layout in Klayout or Magic, and you can do verification in the Magic. Even Klayout, you can do verification, and you can do post-lab simulation again back in XChem. So these are the different things that you can do with the tool. So these have already been added, and we'll do some demos with that. What else? So yeah, so oh yeah, so installation instructions. I have given you all the installation instructions. One additional thing. So in the website we have mentioned you can find installation instructions here. So just go to this link, and here you can, if you have a Windows machine, you can follow these instructions. So they're clearly showing you how to install the tools. And if you have a Mac, then you can follow these instructions. And they're clearly showing all the steps one at a time. And make sure to follow this section clearly. So this display and then design path, these two sections, and then rebuilding the container. So like last three sections, make sure to follow them exactly, so that you can access your designs folder, right? This designs folder, you need to be able to access it from your machine. So make sure to follow these steps clearly. And if you've done everything correctly, yeah, if you've done everything correctly, this is so good. Yeah, so what happens is in your Docker, it will show you like these ports are active. So if you try going to this port, in my one, it's 80, local host 80. I don't know what 5901 is. It's not going anywhere. So localhost 80 is going to connect me to this tool, and the password is ABC123. I think it's somewhere there. They say it's ABC. Yeah. The password is, default password is ABC123. Let me, okay, ABC 1, 2, 3, and you go to your environment directly. Okay, so these are all my projects in FOS designs, and we'll like go through the CMOS inverter in IHP today. Um, so that's basically how you install the tools. And you can try this yourself. So all the instructions are here. We'll update this a little bit more. But everything has been provided. So all the links and everything is here. So you can do this yourself. Um, yeah, but any questions from anyone on this section? Is everything okay? Clear about this part? If you have any sections, feel free to ask questions. Okay. Um, yeah, I think that's everything in this section. So I'll hand it over to Irusha to do the next section now.
Thank you. I'll share my screen. Can you see my screen?
Yes. Yeah, everything's
Uh,
clear, Irusha.
yeah. Uh, yeah. Hello. Good afternoon, everyone. I am Purush Adwan. I am currently third year undergraduate in University of Singapore. Currently, I am working in Singapore University of Technology Design. Yeah. Let's start with our session. So, uh, today's session is about IHP SG13G2 PDK, which is an open source 130 nanometer CMOS technology platform provided by IHP. We will explore its key features, the MOSFET devices, and how we can use built-in test bench and device characterization. Yeah. Uh, Here's a quick overview of what we'll cover in this session. First, I will introduce C13G to 130 nanometer CMOS technology. Then we will dive into the MOSFET types available in the PDK. Finally, we will go through the device characterization where we simulate and understand how these devices behave in different conditions. Uh, let's start with the CMOS technology. Uh, Before we dive into the IHP PDK, especially, let's first understand what a process design key uh, or PDK is and why it is so central to integrate circuit design. A PDK is essentially collection of files and models provided by a semiconductor foundry. It enables us as designers to create and simulate ICs that will be fabricated using that foundry process technology. Think about like this. Uh, if we were building a house, the PDK would be our entire toolbox. That means complete with hammers, blueprints, measurement guides, safety rules, and even sample building materials. Without that, we are just guessing. Uh, Inside the PDK includes DRC and LVS rules, device models, symbols, and schematics, layout, simulation, and simulation setups. So overall, PDK form the bridge between device and fabrication. Without them, designing a real-world IC would be almost impossible. This slide shows a cross-sectional view of the ST13G2 process of from IHP. SG13G2 is a 130 nanometer silicon germanium technology that combines high-speed bipolar transistor with CMOS devices, making it ideal for RF and mixing the circuit design. The process includes up to seven copper metal layers, all insulated with low-K dielectrics to reduce parasitic capacitance. At the top, you will notice that a thick 3 micron layer, metal layer, which is especially useful for routing high frequency signals with minimal resistance. There are also high K min capacitor building to the stack, and the interlayer thickness vary from 400 nanometers to 3000 nanometers. Altogether, SG13G2 is well suited for advanced applications like precision analog, wave transceivers, and high-speed I/O interfaces. Now, let's look at some of the key features and devices supported by the IHP SG13G2 PDK. First of all, it's an open source PDK, which is a huge advantage. It's freely available on GitHub and includes layout generators, simulation-ready models, and schematic symbols. The simulation models are also quite advanced. The PDK uses the PSP model, which accounts for real-world effects like gate leakage, stress-induced mobility degradation, and NQS behavior. Uh, in terms of performance, it supports RF application up to and beyond 75 gigahertz, particularly with the low voltage NMOS devices, which make it more suitable for 5G radar and MA wave designs. The table of the right summarizes the four devices available in the PDK. You will get both high voltage and low voltage. High voltage being 3.3 voltage and 1.5 low voltage MOSFET with isolated options available for noise sensitive circuits. It also includes multiple resistor types ranging from silicide poly for low resistance to high value poly resistance for weight biasing, and WIM capacitors that offer high tolerance and good linearity. Now, let's talk about IHP MOSFET. This slide compares the physical structure of standard NMOS isolated NMOS as supported in the IHP PDK. Standard CMOS devices share a common P substrate, which means all NMOS transistors also share a body terminal. In their lead body effect, leakage, and substrate noise coupled. The isolated NMOS is built into deep in-well, enabling full four terminal operation. Uh, this lets designer independently control the body voltage, which is incredibly useful for the analog and RF applications. Uh, these isolated devices are especially effective at reducing latch-up risk and improving gain stability in low noise circuits. You can see uh, this is the normal CMOS process, and in the isolated NMOS process, there is a deep end where in N plus. Yeah. Uh, this slide gives an overview of how MOSFETs are analyzed and used in analog circuit design. We model them as voltage controlled current sources, especially in saturation, where the drain current is mainly controlled by the gate voltage. In most transistors, usually preferred for speed due to their electron mobility, while PMOS is used in complementary roles for power savings and balance behavior. One of the right you will see on the right, you will see the MOSFET symbols for terminal representation as well as enhancement and depletion mode types. Uh, for analog application like amplifiers or OTAs, we especially bias transistor in the saturation region where the current is stable and gain can be controlled through the transistor sizing. Yeah. Let's talk about device characterization. IHP PDK provides very helpful set of test bench for characterizing device, all available in the SG13G2 test folder in the GitHub. I will show that folder later. You can see that folder in the right side of the slide. Uh, you can load this directly to XM and run NG-SPICE simulation to extract DC characterization, perform transient analysis or front temperature sweeps. One of powerful feature is the ability to change WL or other parameters like bias voltage in the schematic can pre-run the simulation to see how the transistor behave or shape uh, across region like triode and saturation. You can find this display at the link shown here. I will share my screen. Yeah, you can see my web page. Here, this is the IHP Open PDK. Here, this folder, there is command SG13G2 test folder. Here, we have a lot of test files. You can, these are the test file names and their descriptions. You can load them to the command. You can run transient analysis on others. Uh, you can get an idea how they doing this. Uh, yeah, first we run the experiment. Yeah. Uh, here, yeah, an example of what you can expect from running one of the MOSFET technology. This graph shows IDA VDAs for different VGS and level on the low voltage input. It also shows different model phones, particularly slow and fast, and so you can analyze the worst case variation in behavior. This, this kind of analysis is effective when we decide the digital analog block or current sector. And the PDK enabled with this minimal setup effort. Uh, this is another YouTube video, and it will run the simulation, and this is the AC analysis part. He will generate the plot. Yeah, this way you can analyze your circuits and given test circuits, and you can find that in the later part of the paper. To wrap up, the SG13G2 PDK really lowers the barrier to entry for analog and RC IC designs. You get full access to simulation models, layouts, the cells, schematic symbols, and built-in test bench already to go with like XM and NGSpice with Magic. If you are just starting, I recommend to heading over to the GitHub repo and cloning the PDK and opening the circuits in the uh, 13G2 test folder. You can pick the parameters and simulate different MOSFET conditions in just a minute. Yeah, you can try that. Uh, Thank you. I will hand over my session to Pitnaya. Pitnaya, over to you.
Yeah, thank you, Hirusha, for covering about the IHP PDK. So I will do some demos of what Hirusha showed as well. I think Lohan is going to do the next part on Lohan is going to do the next part on the inverter design. So Lohan, you can share your screen.
Okay. Can you hear me? Yeah, am I audible?
Yeah, I can hear you. Yes.
So hello everyone. So I'm Lohan Atapattu, undergraduate at University of Morato Electronic and Telecommunication Engineering Department, and currently doing internship at University of Melbourne, Australia. So I'm very sorry I am not in a position to turn on my video. So shall I share my screen? Allow me to share my screen. Okay. So yeah. Okay. So this is like the practical, most practical aspect of this workshop, like doing an inverter design using open source tools. So first of all, to design an analog circuit, as Dr. Nilan mentioned and other speakers mentioned, you need to have an understanding about how PMOS, NMOS, and other analog devices work, like as deep into physics of semiconductor. But like we need to start at some point, so it's like good to have like your own design, like designing before, like if you don't understand like fully, it's okay to have like do designs, then you can identify what you need to learn, what you need to study, and that's kind of stuff. So to do it, like earlier we didn't have like tools, like all the tools are very expensive, and the universities only had the tools for also for some with some restrictions with like Synopsys gave some tools, but like here as Kip and I mentioned, we have open source tools so to design analog ICs and also digital IC also. So yeah, so uh, after you installing the Docker image as Kip and I told, and basic understanding about the IHP PDKs, you can like go into a design. So I will be doing onwards from that point. So like first of all, this is the Docker image. So I will be starting it from here. Yeah. Okay. Now like this is the terminal, Docker terminal. Yeah. So yeah, we will be in this designs folder, we can create any design we need. So for I'm using Xchem. The Xchem is the open source tool for designing like schematic capturing tool, similar as LT Spice. If you are electronic designer, you are mostly know about that. So similar as LT Spice, this Xchem contains details about the PDKs which we installed, and it allows to like simulate your designs. So yeah, first of all we need to like select the PDK. So I have already like used them, so I have these codes. Like you need to also like in the open source community we have several PDKs. The Sky 130 is a popular one, and nowadays people are heading towards IHP PDK. So that's why we are focusing on IHP PDK for this workshop. So yeah, right now, yeah. So that's how you're going to start your Xchem. You have to select your PDK, and after that you can like select Xchem and open the model. If I select like Skywater, then the Xchem will be like something like this. It's totally different than normal thing. Okay. So I will go back into the IHP PDK and I will open the Xchem again. Okay. Yeah. So I will directly move into the designing of the inverter. So yeah, first we have to like this will be like press this addition button and you will be going to the new schematic, new canvas. So first you can save this. So in this file, in this folder, you can save, like I will be saving this as inverter live version. So yeah. Okay. So this will be the thing I will be saving. So yeah, to things go smoothly, I have already designed inverter. So I will be explaining this while like doing the design. So it's only for the timing purposes. Yeah, like first of all, you when you need designing, you have to like create this snap and create like according to what you need. This is the most popular. Like yeah, after that you can select the models, primitive cells. So primitive cells are the cells which are given by the which are given by the IHP PDK to simulate your design. So primitive cells, they have like capacitors. These are capacitors, the parasitic capacitors, diodes, and other all the kind of analog stuff, the analog models you need to design, they have it as like they which you need to lay out. They are like from the foundry. So this is the model given by the foundry to like design. So these are high voltage PMOSs and these are low voltage PMOSs. So NMOSs, and in CMOS design we use both PMOS and NMOS. So right now I will be using low voltage. Low voltage means the gate source voltage should be like below 1.2 voltage, and drain source also similar as I remember. So yeah. Yeah, this is a P NMOS, so I will like sit here and I will take another one. and low voltage NMOS. Okay. So yeah, sorry about that. I already have NMOS, so I will use PMOS. Okay. So we usually use S terminal as the source, and this S terminal as source in both PMOS and NMOS. So source for the PMOS will be high voltage, and source for the low NMOS will be low voltage. So because of that, we like usually as convention, like when designing, it's easier to design things like which we are already used to see the things, so like that we can like easily get what we have done wrong. So yeah, so usually we create source in the upper part for the PMOSs. As usual PCB designing, also schematics, we use this kind of models like ground in the bottom and the top voltages on the top part. So yeah, see, similar thing goes in here. So yeah, so this is the what we need. So yeah, we need two NMOSs and PMOS, and like these are V voltage sources. We need voltage sources. So yeah, let's like in the primitive cells, they give like IHP PDK cells. So what the XChem does is XChem have separate devices. They allow us to give the voltages, like they are voltage sources, like uh, connectors, voltage device sources, and other stuff, basic stuff we need to do the simulation. They provide us them. And this is the ground symbol. We also need that, but I will now searching for voltage sources. Yeah, give me a hold. These are V source. So you can also like search from here. It's like I was forget about it. Yeah, for V source here, and yeah, you need two of them. Yeah, this yeah, all the things you need to simulate the inverter is all these voltage sources and PMOS and NMOS. So that's why it becomes the hello world in analog design. So to simulate this, we use SPICE. Like I guess you have already have familiarized with PCB like LT SPICE simulation. So similar language like SPICE language, we use that as the simulation language here also. So for to add that codes, we use in here devices, we have code shown. Yeah, these are, we use this code shown stuff. Yeah, models. So this is the basic items we need to design the yeah. Also we need ground symbol. We will use that GND ground. Okay. So there are several shortcut keys we can use. I will tell it also, like to open the like components, we can use Shift I. Oh, so Shift I. Yeah, we can use Shift I. And like for copy items, you simply use C key, and then you can like drag and drop and like place it there. So that's how it works. Yeah. So right now we need to do the wiring. Okay. To do wiring, like it's pretty like it's when you design a circuit, like it's easy to see the connections without like very few amount of wires. If you use very few amount of wires, so to do that we use like net labels in the like normal PCB design, like PCB designs. So like in here also we can use lab pins. Yeah, pins to connect them. Yeah, I will use like those are also in devices. Like in here we can use lab pin symbol. Yeah, this is the design, like these pins will allow us to connect things nice and tidy. So yeah, right now we have the we need to do the main connections, right? So that's the thing we need to do. Okay. So for that, like we will like connect, we will press on the W key on the keyboard, and then the wire pops up, or we can use simply the wire symbol, insert wire symbol, and it will generate wires. Okay. Simply clicking on the escape button, you can escape from the command. So yeah, I will use the wire W symbol and connect those wires. Yeah. In the IHP, in the MOSFET, like usually you see only the three terminals, but in the MOSFET, as we told earlier, when designing IC level, we have like four terminals, like body terminal. Why is there a body terminal? Like we can like have isolated devices or like common body voltage for uh, every MOSFET. So what I'm going to do is having common voltage for every MOSFET. So yeah, like this, this will be our highest voltage. So the MOSFET body will connect to the highest voltage, and the NMOS body will connect to the lowest voltage. So if I have another transistor according to my design, I will be using same voltage. Like you can use like, if you have another MOSFET here, you can use like simply connect this two. Like if I will like go into that, like if you have another like MOSFET here, you can connect these something like this, but it's like it's have separate other things we need to consider. But to keep things simple, I will connect like this. Okay. So for after that, we need to give the gate signal. So what happen in inverter is like when you giving input signal, input high, it will go into output low. So if you give output high, input low, it will give output high. So that's the basic building block in digital design. So that's what we're gonna need. So we have a output in here, we should be giving the input to here. So that's what we are expecting to do, right? Okay. So yeah. Okay. So those are the connections we need. So this will be our VDD. Okay. And we will connect it to here. So this will allow us to keep things tidier and neater. Okay. Okay. So that's how we connect. Okay. Right now the design is complete, but also like we need to show the output. V out. And also to name this net, I will use V in. But by clicking on the Shift R, you can like change the orientation of any object, like V in. Okay. Like I just simply. Okay. So this will be our design, like the basic design. So what we miss, like keep always keep the design saved. So yeah, the other things are like not in like analog domain, they are on like your coding, spice coding. So yeah, so to check a inverter, you can like give a pulse input. So that's what I'm doing here. Like it's a simple pulse input. So this have a code, like this will be a code, like this is the DC and this is 0, 1 to 1.8, and I'm not sure remember that, but rise time, delay time, and other duty cycle and the stuff is there. So what you need to do is like you can like separately think about what you need here, and you can code it. So this will be your voltage source. I will like, what I do, it's for the simplicity, I will like copy this one to this one. So like it will help me to save my time. So yeah, but in designing, what you need to do is like you need to think about the input signal you need to give. Like some signals might need a DC shift, some like in here you need to have a DC shift. Like there are several kind of things you need. So yeah, these spice command you can easily learn, like it's a separate thing to the design, like it's the most common simulation language we use. So it's like there are plenty of sources to learn. So to give like, I will be using like 1.8 voltage. It's like for this design, like when you are designing, the design you will be given a design parameters, like how can you think about like WL ratios and how many transistors you need. So for that you will be given a like specification is like you will like drive clock from this, then the WL ratio will change. If you like driving a heavy load, then WL ratio change according to that, like the other ratios and other things change into that. So like this is like simple workshop. So how to like build on it, you can like when you're designing like real stuff, you need to think about what you are going to do with this circuit. So based on the application, your design will change. Like the most important thing when designing is these parameters, right? So what are these? Like M is number of devices, like L is the length of the MOSFET, W is the width of the MOSFET. So this like this process allows us to 0.13 micrometer, like 130 nanometer length of MOSFET. So if I annotate my design, like length means like these are the source and drain, and this will be the length. So there are several like things you need to consider, like what will happen to the length when the current is high. So there are things, but this will be the length. So and the width will be the other parameter we use. I'm not going to like go into deep. You can always like search about that. And this ratio, like in the when the MOSFET design, you will use the most common equation is half times 1 or 2 times mu n cox yes, mu n cox, like electron mobility and unit capacitance, and w over l times VGS minus VTH squared. So that will be the equation you are using like every time. So yeah, half times mu n over sorry about my drawings, mu n over cox, uh, mu n times cox, w over l, and vgs means gate source voltage, minus vth. This will be the equation for NMOS, and similar to the PMOS also, some yeah, times squared. So this will be the equation of the drain current. So these equations is the most common equation you used, and there is another separate equation for gain calculation. Yeah, you can learn that from during the courses. So what you can like, these are all constants. You need to like change the W over L ratio to get what desired current. Like most commonly VGS is a constant, like uh, you cannot have many VGSs in your IC because you have separate pins and there are constraints, but you can change it. And W over N and VGS is the like changeable parameters. Those are other things are constant. So what we do is like, we most commonly we change the W over L ratio to get high current. Other things are constant. We need to increase the W over L ratio. If the like to get lower current, we use WO ratio low one. So if the current is constant, when WO is high, then the VGS will be low to keep the constant current. So that's how the designers will think, and this equation govern the design. So yeah, So yeah, those are things. So for this design, I will be using like this custom, like I'm not thought about any like application. So I use simply 2.6 micrometer width and 0.13 micrometer length. So the yeah, for using the lowest L is the common practice in like in making the inverter. So for this one 2.6, and like as you can see, like in the PMOS, the PMOS width is higher than NMOS because the mobility of the electrons is higher than the mobility of the hole. So that's why we use that convention. So this is 1.3 and this is 0.13. And so yeah, that's the parameters we need for the design. So yeah, for W or L ratio, this will be 20 times and this will be 10 times. So yeah, those are the parameters we need. Yeah, so we are done with almost our design. So right now we need to have a code shown. So this thing. So how can we change it? Like for this one, you need to like click double tap and like add values to this blah blah section. So what I will be doing is like I am simply copying it and yeah. So sometimes it's happens, sometimes it's very slow. These are open source tools. Sometimes there are errors like these are like millions like those kind of softwares in industry. So there are some errors in these open source tools, but like I guess we can happy about what we have, like. And also like we need to think about the model also, like in the model this file like grabs the parameters from the IHP PDK like values, so the to the XChem. So we will be needing we will need to tell the XChem what model we are using. So that's why we using this one. So yeah, like simply like double tapping and changing the values will allow us to go. Okay. Yeah. Yeah. So what have I done here? So I using a temperature 27 and control save all. This operating point, this will do the operating point simulation. What as you also all know, like if you have done a basic electronic, you will be knowing, you will know, right? The signal will goes on the operating point, but not in this design. In the normal amplifier, the signal will be going on the operating point. So such that we need, so yeah, operating point means like what DC value will it move on, like will it change. So like we need operating point analysis. So to do that we use dot operating command, and here like it shows like DC simulation. So right now I just used, like for that design I changed the VDD also, but for this design we don't need that. I will be only changing the V in, like input voltage from 0 to 1.8 by 1 millivolt. So that's this command by the step of 1 millivolt. And this is a transient simulation. This works as similar as the commenting. So I am not using this command when I use the star. So yeah, so this is a transient simulation. So in transient simulation, I'm simulating up to 10 nanometers using a 10 picosecond time sentences. So yeah, time units. So yeah, this is another like constant defining, like what is the gain of the set. Yeah, that's like gain is like dividing like gain is the differentiation of voltage over currents. You can learn of them about in the course. So like I'm plotting the V out. So for this one, like we don't need that, I guess. So yeah, and I will by saving this, but I will create this one. This is the file which we are saving our data. So yeah, that's what we have done here. So let's see about our on our netlist. The things are good. Okay, I guess things are good. If like we like simply use this one not connected, then so we'll usually tell there is operating. Yep, let's see this. Sorry, I was about to save. Yeah, if we design if you save the design and like check the netlist, then it will like show undriven node, something like this. Okay, so yeah, if then we like connect it using wire, and then again save this. To save, use Control and S. Yeah, and let's click on the simulation. At least then it's not showing any error. So after that, like you can do the simply simulation. To do simulation like smoothly, you can use like waveform graph edit. So I will be adding a graph here. Okay, to like here. I'm sorry about that. I will be adding graph here, and let's do the simulation. Yeah, our simulation has done. Like I'm doing DC simulation here as in the code. This is the DC simulation. All the other things are like commented out. Like I use them because it's easier to code on a single uh, like code shown and use it whether when you need. Okay, I will again like do the save and do the simulation, and let's go on to the waves. Like in the waves, you have to choose what are you doing it here, and this one using this file. Okay, so open it, and here by double tapping that you can like see what's going on. Like yeah, you can choose V out. You can like apply V out, and then you can like see what's the like in the when you changing input from 0 to 1.8 voltages, like here it's 1.8 voltage, 0 to 1.8, then the output will be going out from high to low. So that's how. So like what you can do is like you can change this like this time, like this voltage, like change the sharpness of this curve and stuff like that by changing the W ratio and increasing the VDD and stuff like that. You can do that. So that's where the analog IC designer comes, like how to like change the waveform. So how should be the like this like in the logic design, like these voltages are like as I remember, like these voltages we like think like they cannot like give any output. The computer doesn't know what will be this, it's the high or it's it a low. So yeah, these kind of voltages are not like some from these like things we can like design what we need. So yeah, and I will show you a simple transient simulation also. Sorry for the time. Yeah, a simple transient simulation. Yeah, I will be. Yeah, as you can see, like there are several. Some transient simulation will take like hours. Like I, according to the step size and the time you need to check. Like if I use 10 picosecond time into 1 hour, then it will take like nearly like many long time to like do the simulation. So I will be using transient. Okay, open. So yeah, this will be the output waveform. So as you can see, like yeah, I will be like do the plotting also, anything out. Yeah, netlist and simulate. Yeah, this will be the like much simpler graph. As you can see, like you can check whether what is the rise time, what is the delay time. Like it shows like high rise time, like from this like values you can see like from here to here how much time it will take. Like it will take like these kind of nanoseconds. So that's will called rise time. So you can like change this rise time like by changing the driven current and also yeah, stuff like that. You can design and change what you need from here, and you can make a symbol. And of course later on keep in eye, I will do the how to do the layouting session with this. So yeah. Yeah. Thank you for thank you for listening. Keep me in mind. You can like go into next step.
Yes.
Yeah.
Thank
Thank you.
you. Lohan, for covering the interesting section on the simulation. So let me. Okay, so we only have 2 more sessions to cover. Yeah, we have close to 1 hour, so I think that's good enough. Okay. Right. So I'm going to share the screen here. Okay. So here's my screen. We have covered the design flow. So all the things Lohan mentioned is documented here. So you can follow the same steps to design an inverter, and you can also go through the simulation part step by step. So I've added some additional, so you can find the files that like the inverter files here, the XChem files, and you can also find additional test benches for like doing DC and transient simulations as well here in these 2 links. So I think Lohan covered the DC simulation, so you can see the NOT gate is working when input is 1, output is 0, in input is 0, output is 1. And here's a transient simulation. So you can see that with time when we sweep the voltage, yeah, when we sweep the voltage, this is how the output of the inverter behaves. And there is a point at which the gain is maximizing, as Lohan said. And there's a video as well I've added, which is like this is the first step of designing the inverter, and which covers this design and simulation phase. And in the layout phase is what we're going to go through now. For the layout phase, now that you have designed your inverter, you've chosen your WOL ratios, and you want to kind of put it on the PDK's silicon structures. How do you like go about doing that with open source tools? So for that, we'll firstly look at what is the structure of a CMOS inverter in terms of like the as Sajita showed previously, all of these electronic components in under basic models, all of these electronic components, we can build them on the silicon, right? So the MOSFET as well, like we can build them like this. So how do we put an inverter on the silicon process? So this is how the inverter would look like. There would be 2 transistors. One should be a PMOS and the other should be an NMOS. And the PMOS is like in the diagram, PMOS is located on the top and the NMOS is located on the bottom, because the PMOS is connected to VDD and the NMOS is connected to VSS. So if you look at how PMOS and NMOS transistors are available on the process, it would look something like this. It's a 3-terminal device. You have the gate, source, and drain, but there's actually another terminal called the body terminal, which we don't need to worry about. We'll consider the fact that the body terminal is connected to the same as the source terminal. Okay, so these are the different regions that we want to talk about. So I'll go to those in K layout itself, and I'll show you like each of these regions. And when you come towards the design, this is what we want to sort of achieve, right? You can say this is the PMOS transistor, this is the NMOS transistor. Again, same thing here. As Lohan said, the PMOS transistor is wider. So you can see the green color section is wider here than the green color section here. So it's wider than the NMOS transistor. And also there are like other different types of connections here. So how do we map this to this? That's the art of doing CMOS layouts, perhaps. So there are some more videos here. So I've added videos for you to kind of learn at your own pace. But we'll kind of do a small demonstration today as well for the sake of the thing. And then I'll show you this 3D layout, which is pretty cool. Okay. So I'm opening K layout now. So you just need two things for this to work. You need the K layout and you need the IHP PDK. So in the IHP PDK, this is the IHP PDK GitHub repository. When you go to the IHP PDK, you'll find that they have a folder called K layout. And here they have like files called Python, technology, and these tests. What you're interested in is getting this technology file installed in K layout. So one way to do it is you can, so this is my K layout, and you can, in K layout, you can go to tools, manage technologies, and in manage technologies, you can add technology and you can name it IHP, and you can import, sorry, I think you can directly import, sorry for that. So I can directly import, can go to downloads, okay, add this, sorry. Oh, I think it's okay. So IHP PDK, technology, K layout, and it's looking for this .lyt file. So if you select this, it will install the technology. I'll remove this one. Okay, so it's detected the technology, and I think you have access to everything, okay? Yeah. Okay. That's okay. Yeah, sometimes it's getting stuck, so mm, why is it getting this? Maybe I'll restart this. Sorry. Okay. Okay, layout. Start a new thing here. Okay. So tools, manage technologies, and you can check here. Okay, this is there. So you can see that your technology is active when you go here. So I can change between different technology files as well. So I'm going to stick with this one. So next I need to do is I want to get the cells from this technology file. I want to design the inverter, right? For doing that, there are two ways. One way is to kind of get access to the parametric cells of this technology. So the problem is like I'll show you the what the parametric cells are. Um, 330. Okay. So these are the parametric cells. So in this SG13G2 Python branch, you'll see like the Python cell library, and then you'll see IHP, and then you can see like you can open these as well. Let me open some of those. NMOS code. So here's the parametric cell of the NMOS transistor, and here's the parametric cell of the PMOS transistor. And you have inductors, and you have capacitors, and the D antenna is actually the diode and bond pad. So all of those have parametric cells. So these are Python cells. They're Python described cells .py files that you can use to set up the um, cell itself. I'll show you what the cell looks like. We'll maybe try running one of these. I don't know what's happening. Okay, so it doesn't work from here. So something might be needed to be fixed there. But yeah, I'll try to figure out what's the issue here and fix it. But the same components that are in the parametric cells, I'll show you from this one. Same new panel. So these are the same components that we saw in the parametric cell. So the antenna, um, and bond pad, and like all of those are here as well. Okay, so I'll show you the MOSFETs. This is the capacitor. I'll show you the MOSFETs. This is the NMOS, and this is the PMOS. Okay, so NMOS, if you look here, these are all the layers that are in this PDK. By layers, what I'm talking about is actually we'll go here. So you remember we showed like this IHP stack, and here you can see like layer by layer by layer by layer how everything has been designed, and these are like nanometer level layers, right? So if you look at these layers, like you'll notice that there's back metal. I don't know, some of these layers are. So there's top metal 2, top metal 1, metal 5, 4, 3, 2, 1. So this is top metal 2, VR top metal 1, VR 5, 4, 3, 2, 1. So those are all those layers. And you can see metal 1 is here on the transistor. Okay, so where is it? So this is the transistors. So this is a NMOS and a PMOS, and see metal 1 is connected. So this is the transistor level that we're looking at. So this is the same thing, right? And there's metal 1, metal pin, and then gate poly. So there's a gate poly here, and there's active layer. So those are the like layers that are constituting the transistor. And if we now go back to layout phase, you can see what these layers are. So there's a metal metal layer is required. So you can see the black color thing here connecting connecting upwards. That's the metal layer. We have VRs and contacts. So the black color things are the contacts, and what are connecting the metal and the contact is the VR. So that is there, right? So here's the contact, and here's the here's the contact, and here's the metal, and there should be a VR somewhere. I think the VR is automatically added. Yeah, I remember correctly. As long as there's a overlap between those two, I think the VR is added. So there's those two, and then polysilicon gate, gate oxide, and active diffusion area. So this is the active diffusion area, and here's that active diffusion area, and gate oxide and polysilicon gate. So here's the polysilicon gate, and the gate oxide sort of gets added on the polysilicon gate. Okay, yeah, any questions? Is everyone following? It's okay? Okay. So we have the NMOS. I'll copy the NMOS here. And then we also need the PMOS. So here's the PMOS. The PMOS has something extra, which is the substrate drawing is the substrate, and then there's an N-well. See, this one has an extra N-well PMOS. So you can see the N-well clearly has been added to this one. Okay. And this is a PSD drawing. It's not that important. Okay. All right. Okay, so this is the PMOS. NMOS is there, PMOS is there. I'm just going to add them in the top cell so that I can use both of them the same design. Um, okay. So here's the NMOS and the PMOS. Now, so you saw that this was the gate. So the middle part is the polysilicon gate. Okay, that's the gate, and there's a on the gate you can see there's a that a contact. No, what is the what is that layer? The sorry. Oh yeah, heat transfer. Oh, okay. So this is the polysilicon gate here, and you know that the gates of the two transistors are connected, and Vin is given to them. So basically, it's saying that we have to connect these two gates together, and you can see that gates are connected using the metal one layer, right? So you can use this same metal one drawing, and here I'll just create a box structure, and I'll connect them like that. And then this is the pin that goes into the input. So that's my V in. And what else? The transistors, this guy's drain and this guy's drain are also connected together, P and N. So you can connect the two drains together like this. So if you actually notice here, you see that this is a symmetrical device. So you can consider this side as the drain and this side as the source, or you can consider this side as the drain and this side as the source. So I'll consider this is the source of that device, this is the drain, this is another drain, and this is a source. So the drains are connected together, and the source is connected to VDD. This source is connected to VSS. Here's my VDD, sorry, VSS, and here's my VDD. Okay. If you want, we can use some kind of text to add those in as well. There's a text layer somewhere. Yeah, text. And then size of text 1 and VDD. So that's VDD. I think that worked. VSS. Okay, VDD is there, VSS is there. Okay. And I need more ones. This is input, alignment, right, and left. output. No, not center. Okay, output is this one. Okay, so any questions? So this is VDD, VSS, input, and that's the output. One more thing. So like in order to connect the, where can I show it? Sorry, here, IHP PDK. In order to connect the gate, like this gate to the metal layer, we need to make sure that the metal layer is connected to that, right? For that, I think you have to use thick, not the thick gate oxide. There is a special VR that I think you can use. This is VR1. Yeah, I think different in this one. I think it should be this one. Right, another one. Thick gate oxide. So you can use this VR, I think. This is VR1. I think there's a feature to see the X outline. Let me check if we can do that. No, this is from that one. Okay. Active gate poly metal. I'll check that part and update it, but yeah, essentially you can connect it like that. Oh, there's a question in the chat. In design, how do we know which layer need to use for what? Do we have any guide? Yeah, that's a good question. So, for example, like I'll show you some like very complex designs, maybe. What is the one? Wait, I'll open one. I was looking at this design today. Yeah, I think this. Okay, can you guys see this one? Okay. Here, so you can see that this is a very complex design. And you're looking at this one. This is having everything. I'm trying to see if I can remove the. No, wait. I'll open something easier to show. This is the VCO. Okay. Yeah, this one. Okay. This was better. All right. Okay. Yeah, I get that. So, seal ring එක අයින් කරා. These are diodes. I think this is easier. We are stack. Where's the design here? I can break down. Okay, never mind. So I'll use this one. So here, like they have designed some inductors. So here are the inductors in this one, and like with experience, you'll understand okay, if I'm making an inductor, which metal layer should I use? So here, this inductor has been designed in seems like metal. Like metal 1 is definitely there. Top metal 1 is definitely there. Top metal 2 has top VR2 and top metal 2 has been used. So most of the inductor is in top metal 2 actually, right? These are also inductors. And here's the low noise amplifier. And these are transistors, right? So transistors, you design transistors on the very low, like very bottom of the stack. And in order to connect the transistor to an inductor, what do you have to do? You have to go from metal 1 to VR1 to metal 2 to VR2 to metal 3 to these are again capacitors, and then VR3 to metal 4 to VR4 to metal 5 to there's another top VR1 to top metal VR top metal 1 to there should be one more here somewhere, and then yeah, so it goes up to top metal 1. So here, like this design here, you have to use all those layers to put your, yeah, so this is your capacitor. To connect capacitor to this one, you have to use some levels of metals, and your transistors to connect them to inductors, you have to go use all the layers. So does that answer your question, Harinder? So depending on the devices you use in your design, you have to choose how do I connect my transistors to my capacitors? How do I connect my transistors to my other transistors? How do I shield? So you can add shield around your transistors. See, so here's a guard ring around transistors because this is a RF design. So you can add those as well. And then this one connects to inductor because inductor, this goes up to top metal 1 and then inductor is in top metal 2. So these two are connecting together. Okay, so that's the idea. And this is your inverter design. It's a very basic idea, but yeah, I think I can end my session now. Let me check if I covered everything before I give it to. Yeah, so these are the steps. So you have to try these yourself. I won't be covering all the parts, so there's some more steps here. We'll be covering these in the course as well, but before we start the course, even you can try these yourself. And finally, this is a cool tool to see what we designed. You can see it in a 3D manner. And you can view many types of designs like this using this tool. And here's an inverter as a 3D structure. So you can see these were the two metal layers that I told you, VDD and VSS, up and down. And here's the N well. The gray color thing is the N well. And these two ones, these two ones are the active areas. And on top of the active area, you can see the polysilicon gate that is creating the gate. So that the active area is separated by the polysilicon gate, and polysilicon gate is controlling how much is traveling between these two areas. And you can consider one side as the source and one side as the drain. So you can see they've connected these two sides together with this connection. So that's the drain. And these two are connected, not connected to each other, they're connected separately to the metals. So that's VDD connected to one source, VSS connected to the other source, and here's the input. So one lone thing is the input. And yeah, you can view very huge designs like this. We will show you a quick example. It's a huge design. So you can see like it's massive design. So these are the like types of designs that like will like we want to like get into, not like design inverters, but you can see how much transistors, like all of this stuff in this one. And this is a ADC. If you have heard of these analog to digital converters, this is an example of designing an analog to digital converter. Yeah, and that covers my section. So here's a small document from IHP PDK about like design rules. But we'll talk about these things in the course in detail. Yeah, I'll hand over to Udara to cover the final section, and we'll probably have 5 minutes to discuss the course outline. Udara, yeah, you can take over. Oh, there's a question. Sorry, I'll just answer this question quickly. Can you explain the XChem drawing and the K-layout layering connection? Is anything like netlist import purely draw manually the layout? Yeah, you're asking a good question. So how do I know I draw something? I drew like I have my schematic, and from the schematic I visually understand, and I try to draw the same thing here. And sometimes if it's huge design, how do I know I drew it correctly? So for that, in the verification stage, there's something called run K-layout LVS. So you can run this. This is giving me an error now. I think need to set up some stuff. But if you can run K-layout LVS, I think there's a clear explanation in this video here. Verification and parasitic extraction. So when you run LVS, you'll see that LVS is going to give you like how similar your layout is to your schematic. So LVS is layout versus schematic. And if LVS is passing, that means whatever you had on your schematic is the same in your layout. So that's how you handle that. That's how you know that you did the analog layout correctly. Okay, so that's the answer. And yeah, okay, I'll hand it over to Udara. Thank you.
Thank you, Vikram. Let me share my screen. You can see the screen, right?
Yes, Udara, you can go ahead.
So good afternoon, everyone. Welcome to the last session of this workshop on CMOS Process and Technology. I'm Udara and I'm also a graduate from ENTC, and currently I'm doing double degree masters at Hamburg University of Technology in Germany with my masters in microelectronics and microsystems and MBA in technology management. So what we are going to talk about in this session is mainly on how do we actually manufacture the microcircuits on silicon. So up to now in this whole workshop, you saw how we can draw a schematic, a basic inverter circuit on schematic, and do the layout, and you can extract the final files, which you call as GDS files, which you give to the fabrication plant to actually manufacture the circuit. And in this section, I'm going to quickly give you a short overview of what actually happens in manufacturing these circuits by taking the same inverter as an example, and why it's important to know it even if you go into become a digital or analog designer, or even if you decide on to go into research or into a manufacturing role. It's important that you know what actually happens when it gets fabricated, because the PDK is end of the day provided by the fab, and you have to design everything according to their specifications. So having the basic understanding about both the CMOS, how a CMOS and the technologies work, as well as how it actually looks like when it's fabricated, is important. So to give you an outline of what I'm going to talk about, I'll at the beginning I'll quickly show you how all these things connects in the entire semiconductor value chain, different activities from what we have been discussing and from to what I'm going to discuss. And then we'll start off with the first step of manufacturing. We are extracting silicon and how the silicon wafers come from. And then we'll go into see how the inverter is actually manufactured. So yeah, let's take a ride to the world of manufacturing. First, so just probably to awaken you up, let's take a minute and read this text. This is an extract from one of the most recent books published on the semiconductor industry. You can purchase this on Amazon if you like. But while reading it, try to map these different countries and regions the IC takes its journey through in a world map in your mind. So let's take a minute and read it. I guess you had enough time to read it. So if you already was able to map it, I have a diagram next. See if it actually maps with what you were imagining. What I wanted to show is that this entire semiconductor value chain is distributed all across the world. It's not one specific country or one specific company. And there are different countries who are dominating in different segments of this value chain. In a minute, I'll explain what these different activities are. But you can, at a glimpse, you can see that certain different parts of the world has dominance in certain sections. And probably maybe you can recall what Dr. Sean was talking about in the morning why this is the whole reason for a lot of geopolitical tensions in the world right now also. Take some time to recall about it after the session. But this is the main value chain I want to explain to you, and the value added by different activities. So what we have been talking about so far is mainly about this design phase. It includes digital designing, analog designing, mixed signal designing, everything, all the IC designing part. And that itself accounts for nearly 56% of the entire semiconductor value generated by revenue. And that contains all these big companies, Apple, Microsoft, Nvidia, NXP, all those. And also there is this tool providers like the tools that we are using, these open source tools, and we have now Xilinx, Cadence, all the tools we use. So most of this part is actually concentrated on, mostly centered around US and Canada, where nearly 68% of the designing actually happens in US. But when we go through this supply chain further to the next steps, after you have actually done your IC designing, it comes to the point of doing the fabrication. So we have two steps actually called the front-end manufacturing and the back-end manufacturing. Front-end manufacturing is where we do the wafer fabrication, that is actually printing your design on the chip, on the silicon wafer. And back-end manufacturing is doing the assembly, testing, and packaging, which is basically like doing the wire bonding, the packaging, and everything. So the second largest value-adding activity in this whole chain is this wafer fabrication. And probably you have heard about one of the most famous companies when it comes to this is TSMC. And that's obviously for a reason, because they account for nearly 62% of the entire market share by revenue. And also there are other players like Samsung, Intel, Global Foundries, and IHP also. So some of these providers already have open source PDKs, but most of them still offer their own PDKs, which we can access through the companies only. And two key other players that I want to point out is these raw material suppliers. It includes providing of silicon and also the chemicals which are needed for this fabrication, which I will show why we need that. And then comes the equipment providers. So this looks like a very small part, but these equipment come from just 5 companies in the entire world, with the 3 of them being in US, and the largest one being the Dutch company ASML, who has the monopoly when it comes to lithography machines. And why it's important is these are the equipment which actually make it possible for us to manufacture nanometer scale level chips right now. So all these TSMC, Intel, these fabs need to use this equipment to do their fabrication, which we will see in a couple of minutes also how this equipment are used. So in this, hope you got some clear idea of like how the whole value chain looks like. And in this session, I'm going to explain how the fabrication happens, and I will quickly introduce to you the 5 most important technologies that we use in fabricating an IC. And if you have any questions, please post it in the Q&A, so I'll answer them at the end. So to start off with, let's see how wafer is initially produced. So we all know that we make use of silicon to do all our chip designing. Literally, one of the main reasons why we use silicon is because it's readily available. It's one of the most readily available material on Earth, but also it has other benefits when it comes to semiconductor physics. But how does silicon actually exist on Earth? Not definitely as pure silicon, but it exists as silicon dioxide. And what is silicon dioxide? Basically sand. But can you actually use the sand in your beaches for this? No, because we need to use specific version of it called quartz sand, which of course you can find once again in most of the continents in the world, but only few specific countries are actually providing this as a raw material for semiconductor industry. So you can get the quartz, and this is melted at the melting temperature of silicon, which is around 1400 degrees Celsius. And before going to this fancy looking chamber, at this point, this goes through a rigorous process of being cleaned to get rid of impurities, to get highly pure polysilicon. But then we provide this polysilicon into this chamber, which we call the Czochralski process, after this Austrian scientist who accidentally invented this process. But now we need not polysilicon. Polysilicon is a different lattice formation of silicon, but we need monocrystalline silicon, very pure basic silicon lattice is shown here also. So to get that, we insert this molten silicon into this chamber, and there is a small seed that we insert, which has the lattice orientation that we want in the wafer. And we insert this to this molten silicon and slowly pull that seed up. So when it comes up, the silicon gets formed in the same lattice orientation as the seed. And this pulling up happens very slowly, and it takes like 1 or 2 days for this one ingot to be formed, because we pull it up at a speed like 10 micrometers per second or something like that. And it results in the formation of a silicon crystal, a crystal ingot like this. And to add a small point to it, nowadays we use p-doped silicon wafers because that's what we need for our CMOS fabrication. So during this step itself, we insert boron dopants for the silicon wafer so that it already comes as a p substrate. And afterwards, this is about then slicing the ingots into wafers using a diamond saw, doing the chemical and mechanical polishing, and finally getting the wafers. So typically, a typical wafer size would be 200 millimeters in diameter and 1 millimeter in thickness. So you can imagine how a physical wafer looks like. And it has, so we print a lot of chips in one single wafer and then cut it afterwards to separate them into different ICs. So I hope you got some basic idea where does this all silicon wafers come from. And afterwards, we can actually go into to see how our circuit gets printed on this wafer. Before doing that, we have a video from IHP whose PDK we are actually using with our courses. While going through this video, try to get a glimpse of what are the technologies that they're introducing and note it down, because I will be explaining how it all works during the whole process. But let's enjoy the video.
Welcome to IHP in Frankfurt-Oder. My name is Sebastian and I would like to give you an insight into the IHP cleanroom. Here we make our microchips, and the process requires quite a number of people, equipment and materials from all over the world. In a cleanroom, the environment must be controlled to eliminate all dust. Therefore, before entering a cleanroom, we have to put on special clothing. Gloves, face mask, hood, overall and boots. And now we are ready to start.
Welcome to our IHP cleanroom.
It had a size of 1,500 square meters, and we operated for 24 hours a day for 7 days a week. And we need it very clean because every particle, every hair could destroy our integrated circuit because our dimensions are so fine and small. For the production, we have over 100 tools, so let me show you around. We start with a slice of silicon with a diameter of 200 millimeters. The silicon is incredibly pure, its structure is in perfect lattice. It undergoes hundreds of manipulations to build up structures layer by layer during the manufacturing process. Let's take a look at some of the first steps of chip production. We can use them as an example to see how the whole process works. To remove surface contaminants such as organics, oxides, particles and metal impurities, we use a combination of chemicals in the initial wafer cleaning process. A batch of wafers is immersed in a special etch bath for a short time and then rinsed with water. In this section, we have a large variety of equipment using different chemicals not only to clean the wafers, but also to etch away entire layers of different material. To create a pattern, the method of photolithography is used. An optical mask is irradiated with UV light to transfer the geometric design to photosensitive resist. The first step is to spin coat the resist onto a wafer. This coating technique involves placing a small amount of resist on a substrate. The wafer starts to spin, which spreads the liquid resist over the entire surface, creating a uniform film. The resist-coated wafer and the mask containing the design structures are then loaded into the lithography machine. Once they are aligned to each other, light passes through the mask and the lens system projects the mask 4 times smaller onto the resist. Only one die at a time is exposed to the light, so the whole wafer is fabricated die by die. Once the photoresist has been developed and the exposed parts have been washed away, the rest of the material acts as a mask. A reactive ion etching process is used to transfer the created pattern into the silicon wafer. Reactive ion etching uses a plasma to create ions. These ions react chemically as well as physically with the material to be etched, so they knock off some material to be removed. The advantage of this process is that you can control the etch profile highly precisely. It's a method of choice for creating fine structures. These structures can be visualized with an electron microscope. This helps us to optimize our etching process. Here we see a trench etched into the silicon. Once the structures are created, they can be filled with another material, such as insulating silicon dioxide. This is done by plasma-assisted chemical vapor deposition, which allows fast deposition at lower temperatures. After filling our structures with silicon dioxide, the surface is uneven and must be leveled. We do this by chemical-mechanical polishing, which combines mechanical abrasion with chemical attack. The wafer is held upside down, pressed against the polishing pad and rotated with an abrasive slurry in between. We have 2 different ways to stop the process. One is a blind polishing, so it's stopped by time, and the other method is a stop polishing, so we have a stopping layer where the process stops. The result is an extremely smooth and uniform surface ready for the next steps. To build our active devices and change the connectivity of our silicon in well-defined areas, ion implantation is a very important method. It involves shooting charged atoms into the silicon. We use boron and arsenic ions for implantation, to name but 2. We only need a very small number, like 1 dopant per 100 or 1 dopant per million silicon atoms. It turns the silicon into a p-type or n-type semiconductor. To electrically interconnect our active devices, we use metals such as aluminum and tungsten. For example, a sputtering process allows us to deposit aluminum. This means that an aluminum target is bombarded with charged particles that knock off aluminum atoms. The sputtered material lands on our wafer and forms a conductive film. Using photolithography and reactive ion etching, the film is patterned and the interconnects are created. The processes shown are repeated over and over again to produce our complete integrated circuit. We need over 600 steps for the entire production, which takes about 3 to 6 months. Each wafer is then cut into many small pieces called dies. Dies and related circuitry are chips that make up our modern electronic devices. This is what the microchip manufacturing process in our institute usually looks like. I hope you enjoyed the tour and now have a better understanding of what is happening in the IHP clean room.
All right. So I hope you got some idea of how things actually look like inside a fabrication plant. So, all right. Next, get into business and go through how we can actually manufacture our inverter design that we discussed in the previous sessions in using these techniques that we saw in the video. So this is the schematic that you saw in your in the previous sessions, and this is how it looks like when it comes to the cross-sectional and the top view. So already you know how these connections are made. So this A part is the V in, the two gates are connected, and this metal layer is the V out, where the two drains are connected, and the source is source of the NMOS is connected to the ground, and this is connected to VDD, both these points. So once we have this CMOS basic structure, we can break this down into a couple of masks. So when you submit the GDS file after your layout, what the fabrication plant does is they actually extract the masks from your GDS file and separate them into different masks, which they want to print on the silicon wafer separately. So for the simplicity of explaining, I've broken it down only to 6 masks, but in the actual fabrication, it will be more separately for NMOS and PMOS both. And let's go ahead and see how it all starts. So to initiate the whole process, we need a p-doped silicon wafer, and that's why I said we at the point of manufacturing the wafer itself, we dope the wafer with a p dopant like boron, and we get a p substrate. And the first step we need to do for a CMOS fabrication is we need to create this N-well for the PMOS. That's the first and foremost step we need. And for that, how do we actually manufacture this? First, we need to apply a protective layer silicon dioxide. Why? Because we need only a certain part of this to be exposed for inserting the dopants, while everything else needs to be protected. So we apply a silicon dioxide layer through a process called thermal oxidation. I will explain what happens there later. And then to transfer, like if you remember, the first mask we had was the mask of the N-well from this. So this is the first mask that we are going to use. And to do that, first we need, on top of this silicon dioxide layer, we need something called a photoresist. Photoresist is simply a material which is sensitive to UV light, which is needed for the process called lithography, which we are going to do in the next step. So this is the first most important process that we come across in our CMOS fabrication. And this is the most important process, to be honest. And because this is where we actually transfer our the N-well mask into this pre-substrate. How? By exposing it into UV light. So part of this photoresist is exposed and removed exactly where this N-well needs to be there. And then we can etch and remove the silicon dioxide layer and remove the photoresist also. And the next two steps comes where we do the ion implantation for doping. So once again, I introduced a new terminology here, ion implantation. But both these terms you came across in the video that we saw earlier. But I will explain what exactly happens in this. So up to now, we transferred our N-well mask and doped our P substrate to form the N-well. So the first process that we came through is called photolithography, and probably the most important technology we use in IC fabrication. Photolithography is a Greek term which simply translates into carving pictures in stone using light. So the simple idea is that you have a mask which has chromium coated layers, which is dark, which does not pass UV light through it, and rest of the part which doesn't have chromium passes UV light through it. So here in a glass sheet, you print your mask, let's say for example the envelope, where exactly it needs to be on your wafer. Only part of it is exposed where light should go through it. And here you have your photoresist, which we applied before putting into the whole setup. So this bluish color liquid. This photoresist, when it gets exposed to UV light, it get dissolved. So once you put your mask on top of the silicon wafer and use a UV light source about 200 nanometer wavelength. And once this part of this photoresist gets exposed to UV light, the areas which get exposed become soluble. So you can simply, by just washing the wafer later on with sodium hydroxide, you can remove that part. So the wafer underneath actually gets exposed. So you can do whatever you want afterwards. And that's how the mask transferring happens in manufacturing. So this is the most, like, all your different masks that comes from your design gets mapped onto the silicon wafer using this process. And even though I explained this very simply in less than a minute, this is a highly sophisticated mechanism which involves the most advanced semiconductor physics. And just to give you an insight, ASML manufactured their latest UV or extreme ultraviolet lithography machine, which uses 35 nanometer wavelength UV, and it cost around $380 million. And only a couple of fabs can actually afford to have this machine. And in the next video, I think, we found a nice video of ASML introducing their latest EUV machine. So I'll just give you a quick overview of what it looks like to get a small sense of it. But if you're interested, you can go through the video later on, the whole video.
At the center of this big factory in the Netherlands, in the midst of a months-long assembly process, there's a revolutionary machine that the whole world has come to rely on.
You could see an EUV machine right behind me.
The size of a city bus, but working with atomic-level precision, these EUV lithography machines are the most expensive step in making every advanced microchip that powers the modern digital age. Data centers, cars, and every single iPhone.
We are the only provider on the planet of this critical technology.
These machines are the only way to print minuscule designs on these chips. They cost up to $200 million, and they're only made by a single company, Advanced Semiconductor Materials Lithography, or ASML.
Today, ASML has a monopoly on the fabrication of EUV lithography machines, the most advanced type of lithography equipment that's needed to make every single advanced processor chip that we use today. And this company is one of the most extraordinary organizations in the world. The machines that they produce, each one of them is among the most complicated devices ever made.
In the midst of a chip shortage that's caused back orders of everything from PS5s to Teslas, the need for ASML has never been higher. Its stock has skyrocketed since 2018, while its three main customers, chip makers TSMC, Intel, and Samsung, vie to be front of line for ASML's next breakthrough technology. The price tag for this next machine, which promises to push the boundaries of known physics, is more than $300 million.
It's so expensive that most companies cannot afford it.
While the chip wars rage on, we wanted to find out what's really going on inside the quiet company making the machines that print them all.
This is the optical part of the machine that makes EUV possible.
We got a rare tour inside ASML's clean rooms in California and the Netherlands to see how these machines use precision lasers, exploding molten tin, and the smoothest surface in the world to bring our digital age to life.
I'll stop that at that point, but we've provided the link for the YouTube video in our documentation. So later on, at your own time, you can go through it and get an idea of like how sophisticated these lithography machines are.
At the center of
All right. So I'll move on to the second most important technique that we need for fabrication, which is doping. So doping comes in two stages: ion implantation and diffusion. So why we need doping? Basically to have a source, drain, and all the N plus and P plus dope regions separately. What happens during ion implantation is from lithography, like in making the N well, we exposed a certain section of the wafer which we want to have the N well. Now to introduce these dopant atoms, we use an accelerator which actually sends a focus beam of these dopant atoms straight towards the silicon wafer. So they come at a very with high energy and at a high speed, so that they straight away goes through the silicon lattice. And these atoms, in the way that silicon lattice is formed, they can penetrate through the silicon lattice, and they get concentrated around this part of the exposed area. And depending on how deep we want this well to be formed, we can control the acceleration and the dosage and everything. So for different parts of the wafer, like the N well is more deep and these N plus P plus regions are less deeper than that. So depending on how the parameters we need, we can control this process. And once from our common sense that we know that if we introduce some atoms into a silicon lattice, we are definitely disturbing the structure of the lattice, right? So to get back the original structure and to get these atoms into position, into formation within the silicon wafer itself, we need to do something called annealing. Annealing is simply heating the wafer to a temperature like 1000 degrees Celsius for around 15 minutes. And in this process, once again, the lattice structure comes into its form, and also it helps the dopant atoms to diffuse further and spread evenly, because it's a very natural process. And whenever you have thermal energy, always we know that atoms and electrons and everything moves freely and goes to its very equal position. So that's why we need we do this thing annealing, and it's the whole process is called diffusion, or diffusing everything so that we get a deeper and well spreaded N well. So this process will be repeated in forming the N well, as well as when we are forming our source drain regions for both NMOS and PMOS. I hope you got some idea of how it happens. So let me go on to the next stage of what we need to manufacture next. So there's something called a field oxide. I think we saw this previously also when we were doing the layout. There are two oxide layers we need in a CMOS. One is the field oxide and the other is the gate oxide. Gate oxide, you already know what comes in between the gate and the channel. Field oxide is used to separate the PMOS and the NMOS, because otherwise you will be having PN junctions, right? So that's the last thing we need. So we need to have a thick field oxide, which once again we use silicon dioxide here, which is formed using a process called wet thermal oxidation. So there's a lot of details, like I have given some fancy names like shallow trench isolation. Those are technical terms used in the industry. But the basic idea is that you form an oxide layer in a certain selected area in order to separate these two devices. And how did we select this? Where to have these oxides? Once again, using photolithography. And then we go on to one of the most important parts of our devices, which is the gate and the oxide. So first we deposit the thin gate oxide layer using, once again, oxidation, but this time dry thermal oxidation. And on top of that, we use polysilicon. Polysilicon is once again heavily doped to make it a metal, and that's what we are using as our gate for both the MOS. And then we can pattern it once again using photolithography and doing a process called reactive ion etching, or simply what we call etching. Etching is removing a certain part using certain process, which I will also explain. So now you have we have our gate formed, and in the next step we need to once again we need as the next step we need to have our the source, do the doping for the source and gate. So for that, once again we deposit that the protective silicon dioxide layer and pattern it. So up to now we have the gate structured, the separation structured, and what we need now is to have the source and drain. So we are first doing the NMOS, and the process will be repeated for the PMOS to get the P plus regions as well. Before going to that step, I think I will explain the remaining 3 technologies that I introduced to you here. One is thermal oxidation, which we use for silicon dioxide, the deposition technique called LPCVD, and the final technique, etching. So thermal oxidation is simply, once again, letting silicon react with oxygen to form silicon dioxide. The only thing is that here silicon itself gets consumed. So the silicon wafer itself gets consumed and it forms silicon dioxide. How? There's a chamber like this where we put our wafers in and you let oxygen go in. And when there's oxygen, silicon very easily forms the silicon dioxide. And so this is formed only in the part which is exposed. That's why we always have these protective layers where we don't want it to be formed. And there are 2 processes. One is called dry oxidation, where we introduce only oxygen, while wet oxygen, we introduce both oxygen and water vapor. Why selecting this process is very critical, because we use dry oxidation specifically to manufacture the gate oxide layer. It is a very thin layer and it needs to be extremely pure. The reason is depending on the purity of this gate oxide, the threshold voltage and the leakage current both of a CMOS changes. So that's why we need very pure gate oxide, and there's a lot of specifications regarding this, and it also gets reflected in the PDK specs of an NMOS and PMOS. And the field oxide is done using wet oxidation because it needs to be thick. The other deposition technique, if we want to have silicon dioxide, we mostly use that oxidation. But if we want to deposit some other material, like we have polysilicon and later on we have a couple of metal layers on top. So in depositing all these different materials, we have separate deposition techniques. There are 2 types of techniques called chemical deposition techniques and physical vapor deposition techniques. So right now I will explain only the chemical techniques, but in our documentation, I have provided some resources for the physical deposition techniques as well. As you can understand, the simple idea is that in chemical vapor deposition, the material, in this case, polysilicon, is deposited using a chemical reaction. So you simply introduce silane to this chamber where you have the wafers, and it will using a chemical reaction, it will break out into silicon and H2 gas, where H2 gas comes out and this polysilicon gets deposited on top of the wafer. And there are a lot of control conditions in this, like the temperature, pressure, and everything, which you will learn if you go more deep into this topic itself. And the last technique I want to introduce is etching. That's basically removing certain part of the material you have deposited. How you do it is the most common approach is called reactive ion etching, where you actually bombard your material deposited with some ions, where it will, because of its using the physics concepts of conservation of momentum, it will bombard with the material and remove those ions only in the part which is exposed. So we went through those 5 most important technologies, and you're always free to go through the material and YouTube videos, and I can provide further reading materials if you want to dig more deep and understand them. But as the final stages, we'll see the same technologies are used in doing the ion implantation for the source and drain of the NMOS. And etching away the silicon dioxide, and the same will be done for the PMOS. So I'm not repeating the same steps, but I'm simply showing it here. And as the last step, we need to do the metal, have our metal layers. So at this point, I'm only showing one metal layer, but if you remember from the BiCMOS structure from IHP, there are 7 metal layers on top of this. So this metal formation is repeated couple of times to form each layer one above other. And they have these oxide layers as insulators to separate metal and different sections without to avoid short circuiting. So this is the basic structure on how it comes out as a when you manufacture the basic CMOS. But even though I showed this in roughly like 15 steps, this usually even a simple basic CMOS manufacturing has about more than 50 steps. And when it comes to an IC, it goes for like 100, 200 steps, and it's a months-long process. And it happens under highly controlled conditions. So to finally give you an overview of where we started with the schematic and where we ended up. We started with the schematic, then we went on to the layout, and now I showed you how this actually gets fabricated. So you can see once it's fabricated, a top view of where different components are. And this is just one CMOS, but in an actual chip, you have, let's say, millions of chips if it's a digital circuit. And so this process happens in all these fabs over a couple of months, and that's how you get your final IC packaged in the assembly halls and get it printed. So I hope I gave you, it was not boring, and gave you some overview of what happens in manufacturing. And that concludes my session. Do I have any questions?
I didn't see any questions.
No, right?
Does anyone have questions for Udar?
So I think I can hand it over to Kipinay again.
Yeah. So I've enabled to unmute and ask questions as well. If anyone has questions, feel free to go for it. So you can unmute and ask, or you can send in the chat. So this is the last part. I'll take like 2 minutes to talk about this. So in this workshop, as you saw, like we didn't really do a lot of work. It was just 6 hours, and we only managed to cover like the very fundamentals, but enough for any one of you to get into this field and get started and start learning. So we want to sort of keep like improving the awareness and the knowledge and education in this field. So our next step is to organize this course, which is spanning 14 or up maybe 16 weeks from start of June 1st to end of August or early September. So we have sort of like put the flyer out for the workshop as well. But we'll officially post the workshop sometime next week. These are the topics that we are covering in the workshop. So you can see inverter is just one unit of the 8 units of the workshop. Like we're doing amplifiers, small signal analysis, current mirrors, differential amplifiers, layout techniques. So we'll go very in-depth into layout and post-layout verification. And we're also having a small competition for the participants of the course, which is sponsored by CASIDA joint chapter as well. Yeah, so you can look out for this course, and I think we have, yeah, so the course is priced at 32,500 because it's 16 sessions. Like it's usually twice as long as our usual courses, but you can get discounts, so you can talk to us about the pricing, and we can arrange ways for you to kind of do the course. Yeah, so you feel free to go over this and get back to us with your questions. Yeah, this is the email, so please send us your questions. And yeah, if you have any questions now, please feel free to ask. Otherwise, we'll see some of you at the course, and some of you maybe later at different courses. And also there's a feedback form, so please give us your feedback. We really value feedback. So yeah, the session will be recorded. It has already been recorded, and we'll be posting it on YouTube. We'll email all of you with the feedback form and the recordings next week, early next week. Okay. Any last questions? So it took 15 minutes extra, but yeah, someone wants to. Yeah. Hi.
How the discounts work in this process? It means for the undergraduate students in universities, how the discounts happen?
So if you are an undergraduate student at a Sri Lankan university, you can get 40% of the course pricing, and for getting that, you just need to provide a valid student identification. And you can sort of apply for the course registration and pay 40% discounted rate, and we'll reach out to you for the necessary documents. Does that sound okay?
Yes. The other question is that is the same process that the other courses we get registered in the skills of the process of registration?
Yeah, it's the same.
Okay, thank you.
Thank you for the questions. Most of the modern chip integrated with analog and digital design. Could you explain how they're linked together? So yeah, that's a good question. Someone is asking how analog and digital designs are linked together. So that's called mixed signal IC design. So you have digital design and analog design separately, separately designed, but you put them together for the final design. So I think if you earlier saw the SAR ADC that I showed you. So this is a analog to digital converter. And if you look at this, This one has a digital design at the very top. So the very top is a digital section, and then the other bottom parts are analog sections. So this is a very advanced design. So we plan to do this type of work at the very end of next year. So we have like 3 courses planned for analog IC design. So this is the first one is the basic one, CMOS analog IC design, and then RFIC design, and then analog to digital and digital to analog converter design. So that's the most advanced one, and there we will talk about mixed signal IC design. Okay.
Just to add on to it, I think when it comes to the fabrication stage, there's no difference as analog or digital. That's only in the design phase actually. Like once you get the IC files, everything's the same.
That's true. Yeah. So yeah, he has actually asked together for fabrication. Yeah. So once you get the GDS or like once you get this image of the IC, nothing is different in the fabrication stage. Yeah. When will the next workshops be? Yeah, so the next workshop will be next year actually. So you can follow the LinkedIn page or the social media accounts. You definitely easily be able to see it. And we usually give like 2 months for registering to a workshop. So I think you can probably notice it before the registration process. What kind of support is available for some questions outside of the session time? You can always email us if you want like some kind of guidance or help. I think I'm on LinkedIn. Most of us are on LinkedIn. Dr. Nilan's email is there as well on the course website or the workshop website. So anyone can email us, and based on our time available, we can reply to you. Is analog IC designing? We still do not have job opportunities in Sri Lanka, at least remotely. Synopsys is only in digital domain. Yeah, that's a very good question, which is why we are doing this course and the workshop, so that that will not be the case anymore. If you're a very good analog IC designer, you can find job opportunities remotely, but even if not, India definitely has lots of analog IC design jobs and companies. So even though India has it, the fact that it hasn't reached Sri Lanka is why we were concerned, and why this workshop and the courses that are coming up are crucial, because if Sri Lanka has the analog IC designing talent, then similar to Synopsys, Sri Lanka will also be having job opportunities in the future. So yeah, that's a very good question, and hopefully that will be not be a question 5 years from now. Will the previous courses like okay, yeah, it will be repeated, but maybe like 2 years from now, because right now we are focusing on making new courses, and it will be hard to manage previous courses, like repeating courses and making new courses will take like different times. Any other questions? Yeah, thank you for all the questions. Please send your feedback in the form as well. Any last questions? We will wait for 1 minute.
When we get informed about the start of the course registration?
Everyone will get an email next week. You'll get the links to the recordings, feedback form, and when the course registrations are enrollments have started.
Thank you.
Okay. After completing this course, can we get an internship? So this is connected to that previous question. So there are no job opportunities in Sri Lanka for analog IC designers. So you probably can't apply for an internship in Sri Lanka, but there are internships you can apply for in countries outside Sri Lanka. For example, I'll actually show you something. Give me a moment. I think I shared it somewhere. Yeah, can't find it in my history. Okay. Oh yeah, I think I found it. Maybe it's this. Yeah, this. Not 100% sure. No, not this one. Wait. I make analog. Oh, okay. I found it. Sorry. I was looking at the wrong place. Here we go. Okay. So you can apply for something like this. This is an internship opportunity in analog IC designing for like programmable analog IC designing, which is in Austria. And it was like start date was actually like this week, but like they'll have these kinds of stuff next day. And like what they're asking for, like knowledge in IC design, Python, and like most of the skills are what you can catch up from your undergrad, and they won't like help with simulating or low level IPs for TAs, DACs, and like similar things. Yeah, so this is an example of an internship in analog IC design, and there are many more opportunities like this around the world because there's a huge demand. And that's why we have identified this as an area to develop in Sri Lanka. There's a huge demand, lots of opportunities, and lots of investment. And they're okay with like a bachelor's students are also welcome to apply. So like these kinds of opportunities are out there. So this is one, I'm just sharing. Okay, I guess we can conclude. Thank you everyone for joining this workshop and for staying so long, and I hope everyone got something out of the workshop and enjoyed, and all the instructors worked very hard on developing this workshop, and looking forward to seeing all of you, most of you, at our next workshop next year, which will also be interesting. It will be on radio frequency IC design. It's even more interesting area, and hopefully we can have an interesting session next day. Okay, so yeah, have a nice evening, and thank you, Udara and Marshall, for staying for the entire workshop as well. Okay, I'll end the meeting.